5, and 90. Therefore, the third velocity function is equal to negative 5t plus 90. The negative sign here, class, indicates the nature of the slope of this line, which is negative because it slopes from top left to bottom right. Okay. Now that we have completed the 50 functions, then we're now ready to uh, sketch the 80. No? Solving for the 80 curve. Now, since we have three time intervals, like from 0 to 6, 6 to 12, and 12 to 18, same goes for the 80 curve that we want to generate. Expect three partitions as well, the same with the velocity. Okay. We will start with for a sub 1t, for a sub 1t. On the time interval, t is equals to 0 to t is equals to 6 seconds. Now, to solve for the acceleration function given the velocity function, we're going to, is it to integrate or to differentiate? Class, what do you think? Are we going to integrate or differentiate? Okay, we're going to differentiate. Right. We take the first derivative, no? We have a sub 1 t is equals to the derivative of the first velocity function with respect to time. From the previous slide, we have 1/2 t squared. So 1/2 times 2, then t. Now that's the first derivative, or simply equal to t. This would be our um, a sub 1 function, t. Now, in order for us to graph the acceleration, we need to evaluate, we need to evaluate the values at t is equal to 0 and at t is equal to 6. So here, at t is equals to 0, well, our a1 of 0 is also equal to 0 because that is just equal to t. And at t is equals to 6 seconds, a sub 1 of 6 is also equal to 6 fps squared because this is now acceleration. Using these values, we can plot our a1 of the function on our acceleration versus time curve. That's it. Next is for a sub 2 t, which lies on the interval t is equals to 6 seconds to t is equals to 12 seconds. Okay, we have a sub 2t is equal to the first derivative of the velocity function, the second rather, with respect to time. Okay, our second velocity function is negative 1/3 t squared plus 8t minus 18. Taking the first derivative of this, that is negative 2/3 t, then plus 18. No, not 18, but rather 8. Rather 8. Okay. T plus 8. This is now the acceleration function, no? The acceleration function for our second velocity, which is still linear, no? The same with the first acceleration function. Now, in order for us to know the the nature of this line on this interval, we will substitute value for for the boundaries. Like at t is equals to 6, what will be the value of the acceleration? So a sub 2 of 6 is equals to negative 2/3 times 6 plus 8. Now, negative 2/3 times 6, I think that's negative 4 plus 8. So we have positive 4 FPS. Next is when t is equals to 12 seconds, we have a sub 2 of 12 is equals to negative 2/3 times 12, then plus 8. Negative 2/3 times 12, I think that is equal to negative 8, no? Negative 8, then plus 8, that is equal to 0 FPS. So the acceleration at t is equal to 12 seconds is 0 FPS. Finally, we will generate the acceleration function for our third velocity function. Here for a sub 3t, it happens on the interval t is equals to 12 seconds to t is equals to 18 seconds. We have here a sub 3t is equals to the first derivative of the third velocity function with respect to time. And we will go back to the previous slide. Our third velocity function is equal to negative 5t plus 90. Taking its first derivative, we will end up with negative 5, which is constant. Therefore, we don't need to evaluate this function at t is equals to 12 and at t is equals 18 because we have a constant value na. Meaning to say, in this time interval, the acceleration stays at negative 5 and it does not change. That is how you interpret. Now, let's make a list again of our acceleration functions, starting with a1 of t. From the previous, we have a1 of t is just equal to t. Then the points are when t is equal to 0, the acceleration is 0. Then when t is equals to 6, the acceleration is 6. For the second acceleration function, we have negative 2/3 t plus 8. So negative 2/3 t plus 8. Now, we also solve for the important points now, like at t is equals to 6, the acceleration is 4. So at t is equals to 6, we have an acceleration of 4. Then when t is equals to 12, we have a 0 acceleration. And finally, for the third acceleration curve, this is equal to negative 5 and it applies from t is equals to 12 to t is equals to 18. Now, let us sketch the AT curve. This is A, this is T in seconds. A is in FPS squared. Okay. Then we make three partitions like 0, 6, 12, and 18. And 18. Now, at t is equals to 0, the acceleration is 0. So it lies at the origin. Now, when t is equals to 6, the acceleration is also 6. Say this is 6. Therefore, here, we will connect these two because the nature of the graph is linear. So it's a straight line. This is how it looks like. Okay. This would be our A1 of t. Next, we'll proceed to the time interval from 6 to 12 using our second acceleration function. That's negative 2/3 t plus 8. Now, when t is equals to 6, the the value of the acceleration is 4, which is different from the previous. Because here, class, we transition from the first parabola, which is uh, which opens upward, and the second parabola opens downward. So it does not necessarily mean that the acceleration for the first should match the second. it depends on the nature of the function. Now, for a sub 2, when t is equal to 6, the value is 4, which is slightly uh, lower than the previous. So at 4, which is located here, so we drop 2 units. Then when t is equal to 12, the acceleration is 0. 0. Then we're going to connect this. This would be our a sub 2 t. And finally, when the time interval is at 12 to 18, we have a constant acceleration at negative 5, and that is below the x-axis. So say here, we have a negative 5 acceleration, and it is represented in a horizontal line. So we have negative 5. Okay, class, this is now the equivalent acceleration curve, no, of our given velocity curve. Next, we will proceed to the xt curve, the displacement versus time curve. And since we're given with the velocity and we are going to find the displacement, we will perform integration. Let's start with for x sub 1 of t on the time interval t is equals to 0 to t is equals to 6. We have x1 of t is equal to the integral of v1 of t dt. Okay. We will not use the definite integral because we need equation. No, we need a function so that we can graph. No, so that we can graph this one on our xt curve. We will use the indefinite first. Then we will solve for the c later using the given points. No. Okay, we integrate the first velocity function. That's 1/2 t squared. We have 1/2 t squared dt. Integrating this will become 1 over 6 t cubed, because we add the exponent power rule. Then in the denominator, we have 2 times 3, that is 6, and then plus c. Here, class, our parabolic function from the velocity turns into a cubic function for the displacement because we integrate. When we integrate, we can notice that the degree of the polynomial will increase, because of the power rule. Okay. How do we solve for C? To solve for C, class, we will use this one. We will use this initial condition from the problem that the displacement is 0 at the initial time. So at t is equals to 0, the displacement is also equal to 0. Therefore, it becomes 0 is equals to 160 cube plus the constant, and here the constant is just equal to 0. Therefore, the final function for our first interval is equal to 1/6 t cube without the um without the constant c. Okay. Next, we will proceed to the second time interval, that is from 6 to 12. Okay, since we don't have um enough slide, no, uh, let me add first. Let me add first an extra slide for this problem. Okay, I will present the slide again. Okay, did you see my presentation?
Yes, yes, sir. Yes, sir.
Okay, let's continue, no? Let's continue. We now finish the first displacement function. We'll proceed to the second displacement function. That is for x sub to t on the interval t is equals to 6 to t is equals to 12. Here we integrate x sub to t is equal to the integral of v sub to t and then dt. This is the integral of, let's go back on the previous slide, that's negative 1/3 t squared plus 8t minus 18. We have negative 1/3 t squared plus 8t minus 18 dt. Let's integrate this. We have negative 1 over 9 because applying power rule, then this is t cubed. Then plus, we have 8t squared over 2, so that's 4t squared. And then minus 18t plus constant. Okay. Kindly spot the error if ever I committed some error during the solution process. Okay, this would be the partial function of our second displacement. To solve for c, we'll make use of the values, no? Like at t is equals to 6 seconds, what will be the value of the velocity? No? We can not the velocity rather, but the displacement, sorry, the displacement. The displacement x. What would be the value of the displacement? Now to get this value, we will refer to the first displacement function for x sub 1. So here, no, let's complete the information that at t is equals to 0, x is equals to 0. Then at t is equals to 6 seconds, what would be the displacement? We can solve that one by evaluating our first displacement function at t is equal to 6. Okay, so become 1 6 times 6 cubed, and that is equal to 36. Uh, the unit is feet. No? The unit is feet. That is the value of the displacement, 36. Therefore, we're going to use that value here. So at t is equal to 6, the displacement is 36 in order to solve for c. Let's substitute this one. We have 36 is equals to negative 1 over 9, then 6 cubed plus 4 times 6 squared minus 18 times 6 plus the constant. Okay, use your calculator to find the value of c. And you can use sheet solve, no? Para madali. We have 1 divided by 9, then 6 plus 4 times 36 plus 4 times 36 minus 18 times 6 plus the constant alpha x should solve the the value of c is 24 and the value of c is 24. C is 24. Therefore, our second displacement x sub 30 is equal to negative 1 over 9 t cubed plus 4t squared minus 18t and then plus 24. Next, in order to complete points, no, like at t is equal to 12, you say at t is equal to 12, the displacement is x sub to 12 is equal to negative 1 over 9, 12 cubed plus 4 times 12 squared minus 18 times 12 and then plus 24. Okay, use your cycle to evaluate this one. We have negative 1 over 9 and we have 12 cubed plus 4 times 144. We have 12 squared, then minus 18 times 12, then plus 24. The answer is 192. 192. 190, 192 feet. And finally, we'll proceed to the third and last displacement function. So for x sub 3t, the interval is at t is equals to 12 to t is equals to 18 seconds. We have x sub 3t is equals to the integral of v sub 3t then dt. Over v sub 3, we have a negative 5t plus 9t. Negative 5t plus 9t dt. Since this is a linear function, as we integrate this, the result would increase will increase the degree of this function of this polynomial function, that is of the second degree na siya and quadratic na, no, from linear to quadratic. Okay, let's evaluate this integral expression. This will become negative 5 halves t squared plus 90t plus the constant. So solve for the constant, we make use of the value of the displacement when t is equals to 12. The displacement is equals to 192 based on the the answer that we got from the previous, no, from the previous displacement function. Let's substitute this one. We have 192 is equals to negative 5 halves. The t is 12, no, 12 squared plus 90 times 12 plus the constant. Okay, use your calculator again. You can use shift solve 192 alpha equals, this is negative 5 halves times 12 square then plus 90 times 12 then plus alpha x. Shift solve, the value of c is negative 5 to 8. Negative 5, sorry. We have negative 5 to 8. Therefore, our third displacement is of the form negative 5 halves t squared plus 90t minus 5 to 8. And expect that this is a parabola that opens downward because the sign of t squared, which is the leading term, is negative. Now, we will solve or we will evaluate this at t is equals to 18. No? So what will be the value of x sub 3, 18? Let's evaluate this one. So negative 5 halves times 18 squared plus 90 times 18 minus 5 to we have x sub 3 of 18 is equal to we have negative 5 halves times 18 square plus 90 times 18 then minus 5 to 8 and the answer is 282 class no the answer is 282 feet. And by the way, this is the accumulated displacement no from t is equals to 0 to t is equals to 18. Okay, and I think we get the correct answer no. Let's go back to the previous slide, the initial slide of the problem. So the x sub 18 is 28. We're correct, but we need to generate first the displacement time curve. Okay, we make a list again of the displacement function starting with x sub 1. X sub 1 t is equal to um 160 cube. So it's a cubic function. 160 cube. And then we list the important points no. At t is equal to 0, the displacement is 0 based on the problem. Then at the terminal boundary, we have at t is equal to 6, the value of the displacement is 36. Okay, next, for the second displacement, the equation is still cubic. That is uh, negative 190 cube plus 40 squared. Negative 190 cube plus 4t squared minus 18t plus 24 minus 18t plus 24. Then we will indicate the important points like when t is equal to 6, the velocity, the displacement is 36. And when t is equal to 12, the displacement is 192. So 192. Finally, for the third displacement function, this is a quadratic function. So negative 5 halves t squared, 5 halves t squared, then plus 90t minus 5 to 8, plus 90t minus 5 to 8. Then we indicate the important points at t is equal to 12, the displacement is 192. But when t is equal to 18, we have displacement of 2, 8. Okay, let's generate the xt curve. So x in feet, then time in seconds. Then we make three partitions. This is 0, 6, 12, and 18. Starting with x sub 1, we have from 0, then at t is equal to 6, we have 36. Say, this is the 36 point. And since we have a positive t cube, then it will look like this. Now, like it will increase in this manner. Okay, this is our x sub 1 t. Next, for the second cubic function for x sub 2, it has a negative leading term. Therefore, the the nature of the curve will open downward. No, and we're going to plot the second point because we already did with the first point that is 636. Then for 12, that's 192. We will put here 192. Then at 12, over here. Now this cubic function will tend to open downward. It will be like this. And finally, at x sub 3 is this is x sub 2t. For x sub 3, we will plot the time, no? We will plot the displacement when t is equals to 18. And when t is equals to 18, the value of the displacement is 282. Okay, 282 for here. And as you can observe, this is a quadratic function that opens downward because the sign of the leading term is negative. And it will look like this, class. This would be our x sub 3t. Okay, that's it. No? This is how you generate the displacement versus time curve given the velocity versus time curve. Any question? Class, do you have any question in regard to this problem? By the way, I am not really particular with how you uh how you perfectly plot the curves. As long as uh it is a curve, no, let's say for example for cubic, I would expect that you will sketch a curve rather than a line because it's obvious that the degree is more than one. And make sure that your curve, no, must follow the downward opening or the upward opening. If the leading term is negative, then that would be a downward opening of the curve, regardless if it's cubic or quadratic or quartic or higher order. Must curve downward for negative. For the case of positive leading term, then you have to uh, sketch your curve in such a way that it tends to open the upward direction. Okay, and then for the parabola or quadratic, I think it's obvious if your leading term is negative, it opens downward. Otherwise, it opens upward. Now, if you have a line, make sure to avoid sketching a curvy line because for straight line, it must be a straight line. Okay, are we clear?
Yes, sir.
Sige na, sir.
Okay. Yes. Do you have any question?
Amo bagi plot ang kuan sir ba kaning Desmos ba kaning mga equation
Okay.
sa this kaning x2 x sub 2 kaning
Yep.
negative 1 over 9 t cube.
Mhm.
Ang kuan lagi sir is pasak ay pakuan lagi siya sir sa pa-open upward ang iya kuan ba.
Opens upward.
Oh,
Try to focus from 6 to 12.
ay from 6 to 12.
Oh, from 6 to 12 and not from 0 to I would also
Ah,
kindly zoom in the graph, then try to uh
so 6 to 12.
look from the 6 to 12 na range.
6
From 6 to 12.
hindi na 6 to
Because
12.
in our XT, we're only concerned with the the behavior of the curve, no, from 6 to 12.
Sakto, sakto, sakto. Nay,
Okay na?
oh, sakto na
Naman.
sir. Wara, sa babaw din siya dapat. Wara na sumaw. No,
Oo,
wara na sumaw.
kababaw na siya. But for
So, sakto.
0 to like 6, I think it will curve upwards, no? But for 6 to 12, since we have negative here, so it will curve downwards.
Pinagtagmo mo man siya, kaning una.
Mm-mm.
Sige sir, thank you.
Okay. How about the others? Do you have any other concerns or questions with regard to this problem? Okay, hearing none, then let's proceed to the next topic, which is about the kinetics of rectilinear translation. We'll start with particles, then the last lesson for this one is for rigid bodies. Kinetics. Let's review, no, the lesson from module one. When we talk about kinetics, our analysis here considers the effects of external forces to the motion of our body, and we are going to use the Lambert principle, the laws of motions, in order to solve such problems related to this one. And although we're now in kinetics, we can still use, no, the kinematics equation, because like it will come along with the Lambert's principle, because without the three kinematics equations, well, we cannot uh, forgo our analysis. Di ta makapadayon when we do kinetics. Okay? Ang nadagdag lang ani are the Lambert's principle and the laws of motion. But still, we use the kinematics equations, no, the three kinematics equations. Okay. Under this lesson, you will be able to apply the Lambert's principle, like the sum of the impressed forces is equal to the sum of the um, effective forces. No, impressed force equals effective force. We will use that principle in analyzing and in solving system of bodies undergoing rectilinear translation. But we will start with particles. No? Then after that, we'll proceed to rigid bodies. Okay, so how do we analyze? No, how do we analyze here? This is in general, like it applies for both particles and rigid bodies. Well, we all know that the definition of a rectilinear translation is that all the particles that make up a rigid body, travels at the same speed, covers at the same displacement, as well as accelerates at the same magnitude. Okay, so if that is the case, then we can just select, one particle that would represent the entire object or the entire rigid body, and we will select that particle that is located at the center of gravity. Now, if we have net external forces that acts or that influence the motion of our body, as shown in this red arrow, like we have a net force, then our body will accelerate, no? And then that acceleration vector, which is represented by this green arrow, shall be constructed or shall be put in the center of gravity. Okay? Because we will only consider one particle in order to simplify our analysis. Para di libog ba kag labels anak ko imong tagsatagsa no? If we try to analyze each of the particles, it would mess up the entire analysis. Okay. Uh, for our or for this lesson, we will only consider two-dimensional analysis. For 3D, it's a different thing, and it would make the problem more complex. Now, if you only consider the 2D, no, the 2D part, and as you can see, class, here our body only travels in one direction, that is along the x. Therefore, following the D'Alembert principle, we say that the summation of the impressed forces, which are the external forces, is the same idea when we take summation of forces from your statics. So we take the summation of those external forces that acts our body, and the effect of that is it can produce an acceleration to the body. That is why on the right side of our equation we have here the W over G, which refers to the mass, times the acceleration of this body. And that acceleration vector must be indicated or must be constructed at the center of gravity in this in this particle. Okay. Now, given that this object travels on a single direction only or in a single axis, that is on the x-axis, therefore, the remaining axis, which are the y and the z-axis, it does not have any acceleration or motion there. Therefore, if we take the sum of all the forces that are oriented in these two axes, it does not produce any acceleration because our object does not translate on these two axes. It only moves or translate on the x-axis. That is why the the right side of this two summation no is equal to zero. Okay. Now, when we analyze particles that are subjected to external forces, which makes it accelerate, and since we're dealing with forces here, class, because we are now on kinetics, then it is necessary for you to create an FBD of our particles. That is why let's have a review of how to construct FBDs in order to progress the general steps in solving kinetic problems for rigid body system. The first step is draw an FBD and determine both the known and unknown forces. What are these known forces? These known forces are based on the external forces that are given in the problem. And for the case of the unknown forces, these are forces due to the acceleration. No? And from the Alamberts, we refer that to the reverse effective force, no, the REF, which is equal to the mass times the acceleration. Second one is, or second step rather, we're going to determine the direction of motion, no, if not evident or specified, and mark it on your FBD. Since we are not in the statics anymore, we're now here in dynamics. We need to indicate class, or you should indicate the direction of motion because it matters later in choosing the equation for your D'Alembert. Like, uh, where are you going to um your acceleration? Like, is it in the x direction, or in the y direction, or in the z direction? The direction of motion really matters. Okay. And then note that the direction of frictional force is opposite from that of the object's motion. That's the other important thing, no? When you um, specify the direction of motion, just like this one, no? I specify here the direction of motion, which is to the right. Therefore, if there are any presence of frictional force, then you have to oppose that one. Like, this would be the direction of our frictional force. And indicating the direction of motion, no, also gives us the direction of our acceleration as well as the velocity and the displacement. So like you can put here A, which means that in this direction our object accelerates or decelerates. And it also moves at a certain velocity. Okay, direction of motion class again, denoted by DOM, must be important so that we can uh, identify, the direction of our acceleration velocity. And aside from that, the other important thing is we can also uh, understand the direction of our frictional force because frictional force always oppose the object's motion. Now, the third step, once we indicate all the external forces, then we are now ready to solve the unknown parameters. We can start with the kinematic relations, like if the problem requires us to solve for the velocity, we can use either of these three kinematics equation. Okay. Now we can only use these three keys, if we're given with at least three parameters. No, three parameters like the initial velocity, could be the displacement, could be the time. But for kinetics problem, usually the unknown here is the acceleration, because the only parameter class that links between kinematics equation and the Alambert's principle for kinetics is the acceleration. Remember that the Alambert's principle contains the acceleration, no? Like you have the summation of forces along x. If it has a net force, then it can produce an acceleration, no? WGA. So here we have the acceleration parameter. That is why if the problem requires us to solve for the velocity, well, you need to use first the Alembert to solve for the acceleration before you can solve the velocity. So that is how these two um, these two branches works when we perform kinetics analysis. Now, number four, select the x-axis as positive in the direction of motion and apply summation of forces along y and along z to zero. Now, if the direction of motion is only limited to one direction, you can just assign that direction as x, and then the rest of the forces that are not oriented on the x-axis, let's say maybe it is oriented, or these remaining forces are oriented on the y-axis or in the z-axis, you will just equate that to zero, because there are no accelerations on um, this axis, because it only has an acceleration on a single direction, and that is x, based on your assigned axis. And with that, you can perform summation of forces along x is equals to uh, mass weight over g. I forgot to put here a, for the acceleration. And you're going to do this one class for each body or each particle, because later class we will not only analyze single particle, but we will analyze like more than one particle. And for more than one particle, well, you need to construct more than one FBD. Okay, the last one is, once you finalize the direction, you indicate the axis, no, you list the important key is that you're going to use, then you have to solve for the unknowns, no, because that's the last step. And how are you going to solve for these unknowns? Well, make use of the the equations, no, the available equations. Utilize all the available equations from kinematics, which are the three keys, and at the same time the D'Alembert's principle, the summation of forces at a particular axis. If there's a net force, then it can produce an acceleration. Okay. Do you have any question with regards to the general step?
No, sir.
None? Okay. Let's apply this general step and solve some sample problems. Okay, let's start with this first problem. We are given with a multi-particle system. We have three blocks here, A, B, and the last block, which is suspended, no, in this cable. And let's read the problem. The coefficient of kinetic friction under block A in the figure is zero point 0.3, and under block B is zero point 0.2. Okay, these two blocks have different coefficient of frictions. Now, the goal here is to find the acceleration of the system and the tension in each chord. As you can see, class, we have two cables. Expect that we have two tensions. Like here, we'll assign the cable that connects blocks A and B as T1, then blocks B and this hanging block as T2. And uh, from the problem, it is not specified that this pulley is frictionless, but we will assume that it is frictionless. If it is frictionless, then this P sub 2 is true for both B and this hanging block. However, if this pulley is not frictionless, then we may experience difference in tension, no, between these two sides of the pulley. But for simplicity class, we'll assume that the pulley is frictionless. Therefore, we have a uniform tension between blocks B and this 300-pound hanging block. And for this problem, we have now our answers for acceleration, T1 and T2. We will try our best to come up with these values now later as we solve this problem. Okay, the first step class is to construct an FBD. And since we have three particles here, then we're going to construct three FBDs. Let's start with FBD for block A. And by the way, class, this entire system, since they are connected to each other, class, well, they will move with same velocity as well as acceleration. So they only have one, no, one acceleration, A. Because if we have different acceleration, maybe the cables that connects them maybe have some elasticity or it will stretch. That is the case, then do not expect uniform acceleration. But here we'll also assume that cables that are being used are rigid and not flexible. Okay, let's continue for the FBD. For A, remember that it is inclined at 30 degrees. Okay. The first external force, obvious, is the weight. No? Specify the weight. Then we resolve that one into two components. Here we have the 100. And if this is 30 degrees plus, this one is also 30 degrees. So here we have 100. This is cosine 30. And then the parallel component of the weight is 100. This is sine 30. Next is we have a normal force. No, here we have a normal force N. And then we have a tension that uh, tension due to the cable that connects blocks A and B. And the tension is always away from the object. We will label this as T sub 1. Next, there is a frictional force that exists between the surface of block A and the inclined plane. Therefore, we will indicate that one in our FBD. But before that class, we need to indicate first the direction of motion before we can plot the exact direction of the frictional force because the direction of the frictional force depends on the direction of or it has something to do with the direction of the motion. No, here the acceleration of this object is towards the inclined plane because this 300-pound block that is suspended in this cable tries to pull these two blocks upwards. Therefore, we specify the direction of motion, the OM, upwards. That is also the direction of the acceleration. With this direction of motion, then the frictional force is down the inclined plane. So we have here F sub F or A. Okay. Now, the next step is perform summation of forces. Now we apply the Lembert's principle. We have the summation of forces parallel to the inclined plane is equal to the weight of this block over g times the acceleration. We treat positive if the force acts along the direction of motion. The direction of motion is upward. Here, we only have T1 as positive force, no? T1. But the rest, like the parallel component of the weight, minus na siya. So minus 100 sine 30. And we also have minus the frictional force. And that is equal to the weight of A is 100 over 32.2 times the acceleration. Here, class, uh, we can still solve for the frictional force. No, remember that the frictional force is equal to the coefficient of friction at block A times the normal force. And if you're going to take summation of forces along the normal axis of our inclined plane, we can say that the normal force is just equal to the perpendicular component or the normal component of the weight, which is equal to 100 cosine 30. So we're going to substitute that one here. Mu A is just equal to the weight of A, then cosine 30. Substituting the values, the coefficient of friction for block A is zero point 0.3, so we have zero point 0.3 times 100, then cosine 30. Therefore, we have T1, then minus 100 sine 30, then minus zero point 0.3 times 100 cosine of 30 degrees is equals to 100 over 32.2 times the acceleration. This should be our equation 1 plus. Okay, equation 1. Now, let's proceed to the FBD for block B. Okay, FBD for block B. For block B, still naka-incline, going to indicate the weight. Then we resolve the weight into two components. One normal and the other one is parallel. So here we have 200. Then the angle of the inclined plane is 30. Therefore, we have 200 cosine 30. And here we have 200 sine of 30. Then we indicate the normal force. Then the direction of motion is still upwards. Now, DOM, as well as the direction of the acceleration. Next, block B is pulled, no, with two tensions. One is labeled T2. It is being pulled upwards, and the other one is being pulled downwards for T1. And then the direction of the frictional force is also downwards, which is uh, opposite to the direction of motion. This is F sub FB. Okay, we perform summation of forces again parallel to the inclined plane, that is equals to the mass of block B times the acceleration. So positive if the forces acts upward, up the inclined plane. Okay, we have T2 minus T1, then minus the parallel component of the weight, as well as the frictional force. This is F sub FB is equal to 200 over 32.2 times the acceleration. Next, we will solve for the value of the frictional force, F sub FB. This is mu B times the normal force. And if we're going to take summation of forces normal to the plane, we can say that the normal force is just equal to the normal component of the weight. We have mu B W sub B, then the cosine of 30 degrees. Let's substitute the values. Mu B is zero point 0.2 times 200, then the cosine of 30 degrees. Therefore, we have T2 minus T1 minus 200 sine 30, then minus zero point 0.2 times 200 times cosine 30 is equals to 200 over 32.2 times the acceleration. Class, this will be our equation 2. You can observe, class, we have T1, T2, and acceleration for our unknowns. We have three unknowns. Therefore, expect that in order for us to solve these three unknowns, we need three equations. And I know where can we get the final equation, and that would be on the hanging block. And we will proceed our solution there. No, we will construct the FBD for the 300-pound hanging block. Okay, FBD for the 300-pound block. Here we have the weight of this block, which is equal to 300 pounds, and it is being pulled upwards by T2. And then since this block has the ability to pull these two blocks that rest on the inclined plane upwards, then the direction of its motion is downwards. This is also the direction of its acceleration. Okay, I think for the 300-pound block, yeah, it's easy to construct its FBD because there are only two external forces. Therefore, we can just proceed to the summation of forces along vertical that is equal to mass times the acceleration. And we put a sign convention that we consider positive if it is oriented downwards, which is the same the direction of motion. Plus, in this case, the your sign convention must agree with the direction of motion. Okay. Do not use the conventional way, or use the method what we did from statics, like we always treat for the summation of forces vertical, we treat positive if it points upward. For dynamic class, you're going to base your sign convention to the direction of motion. That is why I highlighted earlier for the general steps that you should specify the direction of motion. Okay, now there are only two forces. The weight takes the positive value, then T2 takes the negative value. That is equal to WC over G. Okay, we will substitute. This is 300 minus T2 is equal to 300 over 32.2 times A. This would be our equation 3. Now, we're going to solve simultaneously equations 1, 2, and 3. Combine equations 1, 2, and 3. And class, we're going to rearrange each equation such that uh, it starts with the acceleration followed by T1, then T2, and equals to the constant. For equation 1, we will transpose the acceleration to the left side, and then for the constant, we will combine this and transform to the right side. This will become negative 100 over 32.2 A. So I have just transposed the acceleration term to the left side, and then we have T1 positive on the left side, already on the left side, so plus T1. Then we will add T2 because there are three unknowns here. For equation 1, we don't have T2, but it's okay because it is valid to put 0 T2 because it will just equate to 0 anyways. Next is we will combine the constant and put it or transpose it to the right side. So become equals 100 sine 30 plus the frictional force point 0.3 times 100 then cosine of 30. This is our equation 1. For equation 2, here class, we will transpose the acceleration to the left side again. This will become negative 200 over 32.2a, then followed by T1. Here, T1 is negative, so we have minus T1. Then T2 is positive, so plus T2, then equal to the constant. Here, we transpose the two constant terms to the right. We have positive na, 200 sine 30 plus the frictional force, that's zero point 0.2 times 200. Then we have the cosine of 30 degrees. And finally, for our third equation, we will just transpose T2 to the right side, and then we will flip the equation. This will become 300 over 32.2a. Here, class, we don't have T1, so we can just add 0 T1. Then since we transpose T2, or we combine T2 with the acceleration, then it will become plus T2. Then what's left is the constant 300. Okay, 300. Now, use the three equations, three unknowns solver in your cycle in order to generate the values of our acceleration, T1 and T2. Okay, let's input this. Go to mode, then select 5, then select 2 for three equations, three unknown solver. We'll start inputting the acceleration, negative 100 divided by 32.2. Then T1 is 1, 0 ang T2. For the constant, we have 100 sine 30 plus 0.3 times 100 cosine 30. Then for second equation, negative 200 divided by 32.2. Then negative 141, 142. Then the constant 200 sine 30 plus zero point 0.2 times 200, then cosine 30. And finally, the last equation, 300 divided by 32.2, then 0 CT1, 142, and the constant is 300. Okay, the acceleration that I've got here is 4.7966 or 4.8 FPS squared. My T1 is 90.1888, 90.88 pounds, and my T2 is 255.31. 255.31. Okay. Does they have question? Let's see the okay. 4.8, 90.91, 255.36, which is very close, no? 90.88, 4.8, okay, 255.31, 55. Okay, not bad. Now, do you have any question?
Sir.
Yes. Or did I mistakenly write some errors?
Sir.
Yep. Go ahead, Kim.
So pagkuha ba sa normal force sir ba? Pwede
Mm. Ipabalik for normal force.
sir,
Okay, for the normal force, you can perform summation of forces normal to the inclined plane. No, this is the
Pwede
symbol
ka. Oh,
or particular. Then, as what I have discussed now from the general step, since in this axis, our object does not translate, no, man siya nag-untol-untol, then uh, the net force is zero. No, the net force is zero. It does not produce any acceleration because the acceleration only exists along the inclined plane. So here, applying the static equilibrium, no, from our statics, we can also put the sign convention positive if it points in this direction, no, which is on the upper direction. Then we can say that this is n minus the normal component of the weight, that is 200 for the case of black bean siya, then cosine 30, and that is equal to zero. Because by looking at the FBD of block B, there are only two forces that are oriented in the normal axis. So here, we can say that N is just equal to 200 cosine 30. And that is how you get the normal force. Is that clear, Kim?
yes sir. Oh. Mao na
Okay.
sir, ako pumunta na sir, natubag na.
Sige, sige, sige. Nice. Who else? Do you have any question? Last, do you have any question?
Sir.
Wala na? Now, if none, since it's already 8:49, it's past 8:30. We'll just end our online discussion here, and then I will schedule another online class, no? Because my plan is to finish the lecture for module 2 in this week, so that by next week we can proceed to the next module, which is all about curvilinear, no? Curvilinear translation. Don't worry, I will share this PPT with the annotations, no? This notes in our Google Classroom. Okay, is that clear?
Yes, sir. Yes, sir.
Yes, sir.
We will just end our online class, no? Just end our online class. The time now is 8:50 because I know there are some of you who are still working with your module exam.
Sir, pwede mamuta na so.
Okay.
Kuan lang ba sa kanilang kung gamay lang ba sa take home ba?
Oh, so when?
Kani bang sa di Allenberg sa pero kanang na force gi-applied nga kuan pina-resultant man nga siya nga style ba? Ang
Mm-hmm.
i-consider po ba ning kanang kuan ano niya sir kanang pag inikuha sa normal force sa kuan ba sa summation sa y ba? Okay.
Yes, yes, because the F there, no, is inclined at an angle. Therefore, it has two components. One along the horizontal surface of the table, and then the other one is normal to the table. So therefore, it can also affect the normal force. Ona siya, Kim.
Sige sige sir, thank you.
Oo. Sige, sige. What else? How about the others? You have any concern? Times more lecture today? Maybe with regard to the module exam? By the way, the deadline for this is tomorrow po, no? I thought karon siyang 11:59. And class, make sure to submit no a hard copy on Friday. So, ha?
Yes, sir.
Okay, so what you're going to do tomorrow is to submit a soft copy, must be in PDF format in our Google Classroom, and then do not throw your hard copy because you're going to submit that on Friday. Okay, so if you don't have any question, thank you, no? Thank you for the 19 or okay 18 students who attend this online class despite of your hectic schedule. I hope you learned something, no, from my lecture today, even though it's online. And yeah, thank you and God bless. So class dismiss.
Thank
Goodbye.
you, sir.
Yes, sir.
Um,
Thank you, sir.